for this first introduction on the slides, I will first talk about what is machine learning, the main concept, then specifically focus on what is Scikit-Learn, the library, and then I give you some context on when and why we would use machine learning in some data-driven organization. So predictive modeling or machine learning is the ability to make some predictions of the outcome of repeated events. So we have to use some observations, past observations, historical record of what we are interested in. And we have to make the assumption that the behavior that we are trying to model is repeated in time. It has some structure that is predictable, basically. We cannot make machine learning on random observations. So the way that we do that is to use statistical tools, mathematics, to try to extract some kind of statistical summary of the historical data and turn that summary into some kind of executable model. So an executable model is going to be a program that you can run on your computers. There are still a bunch of seats there. So you could see machine learning as an alternative to programming hard-coded rules written by experts that know about the phenomenon that you're trying to model. So for instance, if you know the laws of physics, you can write some kind of simulator, give some initial condition, and then run the program to predict what's going to follow. But if you don't know the laws of the phenomenon that you're observing, like for instance, if you're trying to build a recommender system that will recommend movies to users, you don't know how to model the taste of users and how that will evolve over time, unless you're a very good psychologist. And in that case, what you can do is use the historical records, the past movie watching behavior of the users to try to find how the movies are related, and to make good predictions on which movie are going to suit which particular users. In practice, it's not necessarily an alternative to hard-coded written rules by experts, because, for instance, for a movie recommendation system, there is no expert available on Earth that is able to make this kind of recommendation for a population of 1 million of different people. It would be too expensive to try to hire experts to do this. So it's not tractable, and machine learning can fit in that kind of situation. Another rule of thumb on when machine learning might be useful is when the frequency of repeated event is quite high. So you have maybe at least thousands of repeated observations, and maybe millions. And making an individual mistake is not too costly. If it costs a lot, like human lives or millions of dollars to make a single mistake, you might not want to use machine learning because you're going to make a mistake. But for instance, if you recommend a bad movie to someone, it's not that big of a problem. But as long as the recommender system is better than not making any recommendation, basically. Okay, so here is an example to make things more concrete. So assume that you're running some kind of a real estate agency and you have a database of past transactions. So your database has columns with different types of values. So the first column is the type of housing that has been sold in the past. The second column is the number of rooms, so it's an integer. The first one is a categorical variable. The third one is the surface in square meters. Then whether a Boolean flag, whether or not it's good. It's close to mass transit. There is a seat here. There is no more seats. Okay. And finally, there is a final column here, which is the price of the transaction. So this is historical data. So you record it in a database, but just based on the operation of the agency. So the vocabulary that we are going to use to describe this, the structure of this data, is that the records, the rows of that matrix, are going to be called the samples, or the samples part of the training set. the columns that we are going to use as input to the model are going to be called the features. And the output of the model, what we are trying to predict, is the target. And so basically based on these historical records, we are trying to find some kind of statistical relationship between the target variable in this column and the input variable, the features, basically. And so we are going to extract this relationship based on the training samples, based on the statistical distribution of the training samples. Then, if you have new potential customers asking for an estimation of their own properties, you can ask them to describe their properties with the same features that you use to describe the past transactions. And for those new properties, you don't know yet the price because you haven't sold them yet, so you cannot know the price. But then you can use the statistical model that you trained on the historical data to give an estimate on what would be a good price to sell those houses. And you can also ask the model to give you some kind of confidence interval, for instance. So those two records here are what we call the test samples that we are gonna apply the model on those test samples to make some predictions. So the general data flow that we use for predictive modeling is to start from some original historical records. So depending on the domain of application, the original data representation that we have can be very different from time to time. So for instance, you could use text documents if you want to do moderation of comments on a website, or images for image classification from images taken from the camera of a mobile phone, for instance, or for specific sensors in an industrial application. The sound recordings, if you want to do speech recognition, for instance, or structured transactions in a database with columns or in Excel files, for instance. There is no more seats. Okay. Okay. So the original data representation is very domain specific, and you might not be able to work directly to do the statistical analysis of that data. The original data format, the data representation, might not be suitable. So what is important also is that for each of those records in that database, you also have some kind of target labels that you're interested in. For instance, for text documentation, a text document, it could be whether or not a comment is offensive or not, if you want to do automatically moderation, or if it's a spam or not a spam. If it's an image, you might ask human annotators to label what is the interesting content of the image. So you need to record those target labels. For sounds, you need some transcription of what is interesting in the sound. And in the transactions, it could be one of the columns of the database. Like in this case, we just record the activity of the operations. And we have this target column that we're interested in, and we naturally have the labels based on the operation of the system. But in each of those cases, the first step is to extract some kind of numerical representation of the original data. That will fit basically in a two-dimensional NumPy array or a numerical matrix. And the important step is that this transformation is domain-specific, but we need to make sure that those numbers here, they capture the interesting part of that original data. So this transformation, there is no generic way to do it. It's very domain-specific, so you need some domain expertise as a data scientist to know how to do this kind of feature extraction. Nowadays, for sound and images, for instance, there are generic ways to do that are machine learning driven, like neural networks. But for many other domains, you really need some kind of domain-specific expertise. Once you have these numerical feature values, feature vectors, you can use a generic machine learning algorithm, such as the ones that are provided in Scikit-Learn. And the result of that computation, of applying the machine learning to the feature vectors and the labels, will result in some executable model, which is a program that you can You can save on the hard drive and move it to another machine, or maybe deploy it on a mobile phone. And then you can forget about this and only focus on the model. The model will take new observations, the new recordings with the same original data representation. You need to apply the same feature transformation, feature extraction step. If it's not the same as this arrow here, the model is going to output meaningless predictions. But if you apply something that is consistent and repeatable, then the model will be able to predict the expected model. It's going to be complicated. I do not sign in, so I can. Okay. But there is a seat here. But okay. Maybe we can have an additional chair. Okay. All right. So all these operations, you could, for instance, if you have a small data set and you want to do some kind of linear regression to extract some trend from the data, especially if it's a transaction log that is naturally represented in an Excel spreadsheet. Maybe you can just transform the columns to do some parsing of the dates or stuff like that, extract some features in new columns, and apply some linear regression routines from Excel to extract your model, basically. If you want to productionalize this, to make it possible to deploy that as a program, it's better to use a generic programming language such as Python, so that you can package it as a software, run tests, deploy it with a continuous integration system and stuff like that. And furthermore, Python is able to scale to a larger amount of data, like gigabytes of data in RAM easily, whereas with Excel it might be problematic. And typically, if you want to do that in Python, you can use the pandas library to do what is data transformation, extraction, feature extraction, and stuff like that. And then use Scikit-Learn for the mathematical part, the statistical predictive modeling part. If your data is very big, the original data transformation might not fit on a single machine in memory. In that case, you might want to use some kind of big data system, like a Hive running on Hadoop cluster, which is basically some kind of SQL engine that run on distributed operations on the cluster. But there are many alternatives to do that. And generally, when you extract the feature vectors here, even if the original data might be very big, the statistical summary that you extract as feature vector for machine learning might be much smaller. And if it's the case, then you can use Scikit-Learn to build a model by loading the resulting feature vectors in memory and running Scikit-Learn naturally. You can, as an alternative, use analytics database on the cloud, for instance, such as Redshift or Google BigQuery or stuff like that, and do the same. And this is very common pattern. And also, you can use alternative if you don't want to use Python. There are also, for instance, Spark that can do both the data preprocessing part and also has some features for machine learning. And nowadays, you could also use Dask for the scalable data preprocessing part and Scikit-Learn for the machine learning part. And this, we are going to present it a bit during the conference. So here are some typical applications for real-life machine learning, predictive modeling. So those are all users of Scikit-Learn. They publicly communicated about their use of Scikit-Learn. So for instance, the New York Times has a team of data scientists that works on modeling the virality and engagement of the readers, the virality of the news and engagement of the readers. Airbnb is using a lot of machine learning to do fraud detection or pricing modeling for apartments. Spotify is building a recommender system to build personalized radios based on the listening behaviors of the users to build automatic playlists that are personalized for each individual users. Birchbox does a lot of inventory forecasting and trends detections in fashion or in any other items. You can also use machine learning to do predictive modeling of the operation of a system, of a complex industrial system. And in that case, the goal is to build a model of the regular operation of the system. And as soon as you detect a drift, then you can detect that there might be a problem. And if you let it happen without intervention, that might lead to some kind of accident that might be very costly. So you can send a maintenance team before the accident happens, and this is what we call predictive maintenance. And for this kind of operation, you could use what we call anomaly detection, which is a family of machine learning algorithms. And finally, there is a OkCupid that has a weird particular case of a recommender system for personality matching for a dating website. And there are many other applications, like fraud detection, churn. Those are very common applications. So this is all a business application, but here at SciPy, it's maybe more a scientific audience, and so you can guess that machine learning and Scikit-Learn can be used also to solve, to help solve scientific application in astronomy, genetics, or whatever. Okay, so now Scikit-Learn. So Scikit-Learn is an open source machine learning library. So it's written in Python because it's SciPy. We rely a lot on NumPy for the arrays and linear algebra routines, on SciPy for some data structures like sparse matrices, and also for optimization algorithms. And we also have some quite extensive use of Cython to be able to accelerate some very compute-intensive algorithms that do not that are not naturally expressible using a combination of vector operations, such as what we could do with NumPy linear algebra operations. So NumPy is very fast as long as you're doing NumPy array operations like a vector matrix multiplication, for instance. But sometimes you need to do nested for loops for algorithms such as decision trees, for instance. And in that case, NumPy is not, cannot be used to accelerate the computation. And in that case, we use Cython. The main feature that is very interesting in Scikit-Learn, I think the reason why Scikit-Learn became popular is that when we designed the library, we made a lot of effort to ensure that the API is very simple. The public API is very simple and very homogeneous, so that we have many machine learning algorithms that are implemented in the library, and most of them, they will implement two of those methods, fit and predict or fit and transform. We will explain later what it means. So this is, I think, what makes Scikit-Learn very interesting. And finally, we also provide some additional tools like model assessments to evaluate the quality of a model, the predictive quality of a model. Model selection to automatically select the hyperparameters of the model. We will also present that this afternoon, I guess. And also how to build ensembles of models. For instance, some models like decision trees, they are not very good when you train them individually, but if you train a big ensemble of them, they are much more accurate. So if you have questions so far on everything that I presented? No? Can you say again what Cython is used instead of NumPy? So Cython, we use it whenever we need, you have a, typically when we have two nested loops that run over many iterations, like millions of iterations for each of them. Some operations, like matrix multiplication, you can express them and compute them very efficiently using NumPy, because NumPy under the hood is using a BLAS implementation, so linear algebra routines. But some operation like making prediction or training a decision tree algorithm, it's not a vector operation. So it's iterating over a column of values and computing entropy and stuff like that, but it's a sequence of scalar operations. And in that case, NumPy cannot be used to accelerate the computation, and we need some kind of compiled level native programming language to do that. So Cython is basically some kind of extension of the Python syntax that will be converted to a C program, and that will be compiled using GCC or another C compiler. and then be embedded in the Python program as an extension. Alternative to Cytons include NumPy, for instance. Nowadays, we could have used NumPy. When we started the Scikit-Learn project, NumPy was didn't exist, so we started with Cyton. NumPy is more dynamic because it can compile on the fly, whereas Cyton you have to compile ahead of time, which has pros and cons. But we are reasonably happy with Cyton so far, so we don't plan to switch anytime soon. But if we were to start the library nowadays, maybe we would have used NumPy instead.
So it's just like JSON, right?
Like what? JSON?
The Java implementation of Python.
Not exactly, because I think the Java implementation of Cyton is still an interpreter, whereas here it's really a compiler. Like it is in a new kind of program that is, Cyton generates a C program that is compiled, and then it's native code that is an extension. But yeah, maybe JSON, the JVM is able to do some kind of optimization at runtime, but I'm not sure how much they can do. So if we take the predictive modeling data flow that I presented earlier and just put it vertically, so we start from the training data. So here the feature extraction has already been done. And so the trained data is an NumPy array with 2 dimensions, the number of records and the number of features. And we also have a single, for instance, vector for the training labels for each of those records. And so this is also a NumPy array. So we call the inputs X and the output Y. And X is 2-dimensional NumPy array, and Y is a 1-dimensional NumPy array of labels, target values. And so to build a label in Scikit-Learn, we just import a class from one of the packages of Scikit-Learn. We instantiate the class by giving some hyperparameters. And then we fit the model on the training data. Once we have done this, the model is being modified in place, and we can call predict on new data. So this new data has the same number of columns as the training set. So it's also a NumPy array with a 2-dimensional NumPy array, basically. And this time, it will return an estimation for Y. There is no room left. He can sit in the floor in the stairs, but. And basically it will return a NumPy array as the output for the predictions. And if you have the access to the true labels for the test set, then you can compute some performance metric for the model to see whether or not your model is able to generalize on new data. So we could also compute the accuracy score on the training set on X-train and Y-train. But generally, it's much less interesting because we want to have a model that is able to make good prediction on future data that we don't have access at training time. So as I said previously, all the models in Scikit-Learn have a very homogeneous API. So here, this is a very simplistic Python program that does exactly the same operation, but with a different model. This time, we use support vector machines from sklearn SVM. We create the model, we call fit, we make some prediction, and then we compute some performance metric. Here, we use F1 score instead of accuracy, which is just another classification metric. So because the model has a fit and predict method, it's all the model for classification in Scikit-Learn have the same fit and predict method. So you can replace that model by another classifier in Scikit-Learn, for instance, logistic regression. And only the first 2 lines need to change, and the rest of the training and prediction and evaluation are the same. Like if I switch between the 2 slides, you can see that only the first 2 lines change. And if you want to try something that is more complex than just a linear classifier, you can use a random forest, for instance, and again, only the first 2 lines change. Oops, sorry. So why we have so many machine learning models, why there is no one good model that works everywhere? It's because most of those models, they make some strong statistical assumptions on the distribution of the data and how the labels are related to the input samples. So here I have 3 toy classification problems where the goal is to predict whether a dot will be blue or red based on the location in a 2D space. So the input features are 2 continuous variables that are the x and y axis on this 2D plane. So the first data set, you have 2 groups of dots that are nested in one and into the other. Not overlapping, but there is a half moon, so basically plugged one into the other. The second data set has the blue dots in the middle and red dots all around, plus some noise. And the last one is 2 blobs, blue on the left and red on the right, but there is also noise, so they overlap a bit. And so you can see that in the first column here, we have a machine learning algorithm which is called nearest neighbors classification, K nearest neighbors classification. And so you see that it's able to find a statistical decision function here that find the boundary between the 2 areas. And here it's able to identify that in the center there are the blue and outside there is the red. And some kind of straight line here in that case. So this model is some kind of database that can generalize by computing distances to new data points. But it doesn't make any strong assumption on the structure of the data, and in most cases it's able to find approximately good separation. But you see that the decision boundary is very noisy, so that might be a problem. Here the second column is a linear model, and you see that the boundary that separates the blue region from the red region is a straight line in the 2D space. And so especially in that case, making this assumption that there is a straight line that separates the blue from the red is completely wrong. So in that case, it's making a big error. Like the quality of the predictions here are very bad. However, here, it's the correct assumption because it's the best way that you can separate the blue from the red. So here, this model is the best, and it's also the fastest to train because linear models generally are really fast to train. So it's a good baseline to try first. And there are also, for instance, support vector machines with a RBF kernel that is basically some kind of smooth version of k-nearest neighbors. You can interpret it this way. And in this case, you can see that the decision boundary has much less noise, so it might be better in all those cases. But maybe in high-dimensional data, that might not always be the case. You also have decision trees here in this column and random forest next to decision trees, which is basically an ensemble of decision trees. And you can see that it's kind of good in most of them. And there are many other algorithms. I won't cover them all. The main point here is that depending on the assumptions that you can make on your data, sometimes a linear model is going to be the best one that you can get. Other times you really need some kind of non-linear models like decision trees or a support vector machine with a non-linear kernel. Otherwise you will get bad predictions. And we will see in the notebooks how to evaluate those qualities. So, yes? So the colors here in the background are basically the predictions of the model. See, if you take a new point in a location that is not a location that you have observed in the training set, how the model will predict the class. And if it's dark red, it's going to be very confident that it's a red location. If it's dark blue, very confident that it's a blue location. And if it's whitish, it's going to be not very confident. So it's going to give you a probability of 0.6 that it's red, for instance. And you can use this confidence level also to decide not to make a prediction where you're not confident enough and you prefer to give no answer than a bad answer, for instance. Sometimes, depending on the application, it might be a good idea to do this. So if you want to know about all the models that are implemented in Scikit-Learn for classification, regression, clustering, dimensionality, reduction, model selection, and preprocessing, we will explain what those means in the tutorial today. But there is also extensive documentation online. I think this is another reason for the success of the Scikit-Learn project is that from the beginning we decided to document everything. So we reject pull requests if the documentation is not up to date. And I think this makes also it a very good resource to gain deeper knowledge on how the machine learning algorithm work, and in which case they work and in which case they tend to fail. So don't hesitate to use this, and you can just Google, and most of the time if you Google Scikit-Learn something, you will find the documentation. So now let's step back a bit and think about where to use predictive models. So assume that you are running some kind of a data-driven organization. So the input for the stream of data that you will collect is the user activity of your application, if it's a mobile app application or some desktop application or workstation application that is connected to a network. Or sometimes you don't have users, but you have a network of sensors in an IoT application, for instance. But in all those cases, basically each of those client components will emit a stream of events that you can collect in a distributed event log with queues. That will basically make sure that you record all the events for the users. Even if one of the machines here dies, there is some kind of redundancy. And make that stream of events categorized, available to different kind of services in your application. And basically, it's very often the case that if you have a high throughput of event collected from the client applications, sometimes you need to make very quick decisions. So you will have some kind of stream processing system that is also distributed for redundancy and scalability, that is being to make transformation very quickly and to output the result in some kind of database that is serving a web user application web interface, for instance, or a mobile app. So this is some kind of online transaction processing system, online database, and that answer the query of the user to refresh a page. So for instance, if you consider a Twitter application, so if some user use a mobile phone to tweet, you will send the tweet to this system here to make sure that you don't lose it. Then process it, like find the list of all the followers that should see the tweet, and then store it in the database in the timeline of all those users. And if any of the followers refresh the page, it will ask this and see the new tweet collected with all the other tweets that have been tweeted recently. So this typically takes less than 1 second or a couple of seconds maximum. And then you typically have some kind of long-time batch processing system that is able to perform operation on histories of collected events. So for instance, the first step is to store the data in some kind of structured distributed storage. It can be unstructured, actually. It can be just a HDFS distributed file system. And then you have, on top of that, a distributed batch processing system that can aggregate, compute statistic on all the historical part of the system and output some kind of statistical summary. So these operations, you can store the result in a structured database for fast analytical queries. So if you have business analysts in your organization, you might want to output some kind of dashboards for running the company and seeing how the trends of the sales evolve in different regions of the world, for instance. But you can also use this analytical database or directly this distributed batch processing system to extract features for building predictive models. And predictive models, they can also output some kind of forecasting for the business analyst, but they can also be used for making recommendations to kind of enhance the application. For instance, for Twitter, you can highlight the recommended tweet, like have a statistical summary of the most important tweet. And also you could use the predictive models, embed a copy of the predictive model directly in the stream processing system for automated moderation, like spam filtering also, so that you don't store the tweets that are spam, you rejected them from the beginning. So to do this kind of architecture, this is really like a pattern that you would see in many organizations. There are standard open source systems to do each of those steps. Like for instance, for the distributed queue system, you can use Kafka. For the streaming system, you can use Apache Storm or Spark Streaming or Apache Flink. For the database that stores the result and is very fast to answer the queries, you can use HBase or Cassandra or stuff like that. For distributed system for the storage, the long-term storage, you can use HDFS on Hadoop or some store on Amazon S3. You can use MapReduce Hadoop for batch processing system, Redshift as an analytical database, Scikit-Learn, for instance, for machine learning, and so on. But you can use other combinations, like Spark can do many things, so it's quite popular. And you can also use it from Python. I think I will stop here for the slides, and now we're gonna switch to the notebooks. Okay. So first, I hope that you could all git clone this and get that folder. As I've said previously, we made some changes yesterday. So if you use Git, you can do a Git pull to get the latest changes. Otherwise, don't worry too much. The changes are very small. So there is a bunch of notebooks. The first ones are introductory, and in the afternoon we will focus on the last ones. So we will also so the first notebooks are just summarizing also some of the concepts that I've presented in presentation, and then we will also introduce how to use the scientific computing tools ecosystem from Python to make sure that you are comfortable with everything. So Guillaume is gonna give you
Okay. So hi everyone. So I think that the first notebook Olivier already introduced extensively how you can use machine learning. So that will just be like a wrap up of what he said and the small details, for instance, on the data set that we'll use during the day. Okay, so it's specific. So what is machine learning? Olivier already speak about it. So we have usually two phases where we try to train a model and learn the models. And then the second phase where we're trying to test our model and how good it can generalize. So we have a training phase and a generalization phase. So to do that, usually we need data. And the one that we'll use in the first steps is a data set which is called IRIS. So it's a biology database of only 150 samples. So usually it's a toy data set, okay, it's to play around. And it was used in the times to actually differentiate three types of iris. So the setosa, versicolors, and virginica, which for anybody like me, I cannot even see the differences. But for people which are used to it, because they look at the sepal, so one type, I mean, you have the petal and the sepal, which are the two parts of the flowers, and they know, with the size and the width and the height of those, they can actually differentiate the species. So a lot of the thing at the beginning will be to, for instance, play with this data set and try to classify those. So how do we basically represent our data sets? Olivier already mentioned it. We have a kind of a matrix where each row is actually a samples, and a features is a column. So here the feature for this iris datasets, is, for instance, the width of the petals. A second column will be the height of the petals, and then the width of the sepal and the height of the sepal for the two last column. Okay? So we have, for this dataset, 4 features, which just represent the dimensions. We could add several features, for instance, colors and stuff like that later on. So then there's 2 ways of doing machine learning, and one is classification, the other one is regressions. So classifications, typically the one of the flower, when the target, what we try to classify is actually a category. So for instance, one of the 3 types of flowers, or for instance, classify spam vs non-spam. That's the categories. And the second task or problem is regressions, where actually our target is a continuous variables. So for instance, from some sensor, you want to predict the temperature of tomorrow. Okay, so temperature will be a continuous variable between 0 and here a lot of Fahrenheit. And you will try to find a point there, okay? So is where you have, and those one, because you will use the target, so you will learn you have X and you have a corresponding target, you will learn a model that will find the relationship between both. And the second type of machine learning that you have is unsupervised learning. So you just have your X, you don't have any target, and from that you will try to find a structure inside the data themselves. So in this case, we have this type of taxonomy, so where you have machine learning, unsupervised learning, and supervised learning. So we spoke a lot about like classification, for instance, with the flower case, regression for instance, estimating temperatures. We have something a bit more ranking when you want to make recommendations system where you want to say that this is better than this other, I mean, this movie is better than the other one, so you have kind of this. And in the unsupervised case, you have tree family. So Olivier already spoke about anomaly detection with the predictive maintenance, for instance. And the other case is more to simplify the representation of data. So clustering would be to try to group samples together to reduce the complexity. And the dimension reduction could be to reduce the number of features. So find, if we have a space with a lot of features, we want to find a subspace with a smaller feature where we just project into that subspace. And we can use this, for instance, for visualization. So imagine that you have 50 features and you can see only 2D. With your eyes, you could project this into 2D and then see if there is a structure there in 2 dimension only, okay? So that's about these things. So do you have any question on those? Yeah.
You mentioned targets, and then you mentioned labels. So are they the same thing?
They are exactly the same things. So usually we sell, I don't know if we sell labels for classifications.
Yeah, I would say labels is more for categorical variables, categorical targets. And when you do regression, it's a continuous variable. So you could call it a label, but maybe it's an abuse.
Yeah, it's an abuse. Okay.
And also sometimes when we do regression, we can have multiple targets at the same time. You can to predict a price and a temperature in parallel or something like that. Just to add some point about this. So sometimes unsupervised learning is used to kind of find a simplified representation of the data that you can use to gain some insight as a human to see the data set. Like if you find groups of users for marketing purpose, for instance, you can simplify your audience and present that in a slide deck to business people. Or dimensionality reduction is useful for visualization to project in 2D space. But it can also be used as a pre-processing step for supervised learning. So this is another application of unsupervised learning, is to find a new representation of the data without the labels. And then you hope that it's going to be useful if you stack a classification model on top of that new representation, for instance. So this is another application of unsupervised learning. So.
Scikit-Learn offer tools for both unsupervised?
Yeah.
Yes.
Yeah, both things. So in the web page that he showed, you have the classification of unsupervised learning, so like clustering methods and classification methods and regression methods. So you can easily find which one you want to tackle down. So now Olivier will start with how to use a notebook with tricks and shortcuts.
So if you open the second notebook, maybe it was a bit quick, but this is notebook number 2. In the list, it's this one. So here I decided to hide the toolbar, but if you use the traditional Jupyter notebook, you have this toolbar. If you use Jupyter Lab, you have a similar toolbar. It might be slightly different. But in both cases, you have a button to execute the current cell and move on to the next cell, which is this button. In practice, I would recommend not to use the mouse and the click, and to try to learn the shortcuts to do the same. So I will just hide this because otherwise it takes too much space. Okay. Okay. Something that is very also important is that Jupyter gives you the ability to introspect the API of functions or classes that we are going to use. And for instance, you can use Shift plus Tab when you open some function. And it also makes it possible to read the documentation using the question mark. Oops, sorry, I didn't mean to commit this yesterday. I'm gonna give you some keyboard shortcuts that are very useful for Jupyter. So first, to get the list of the keyboard shortcuts, what you can do is press Escape to make sure that the selection of the cell is in blue mode here, and then press H. And then you see all the keyboard shortcuts that are available. And there are two groups of keyboard shortcuts, some that are for the edit mode and some that are for the command mode. To go into command mode, you have to press Escape, and basically the selection will be blue and you're in command mode. If you click on a cell or if you press Enter on a cell, you will enable the edit mode of that specific cell. So it's very important to know in which mode you are. So first, let's go into the blue mode, command mode, by pressing Escape. Then you can press B. So when you press B, it will insert a cell below your current location. If you use the arrow keys, you can move the selection around. And you see here we have a code cell where you can write Python code, for instance, print test, and execute it by pressing Shift Enter. Okay, so you can move the arrow back to the original location on the same cell and press Enter again. And you see it switches to green mode. And then you can, if you move the arrows here, it's you can move around horizontally in the text. If you press Enter here, you have a new line, print another line, for instance. And then press Shift Enter again, and it moves on to the next one. Okay? So something that is weird here is that I pressed Enter also in this cell, and you see that here I have this weird representation. If I press Shift Enter again, it's executing the text basically, and it's basically rendering the HTML. So if I double click here or if I press Enter, you see how to edit the text, because this cell is a markdown cell. So you have two types of cell, either the code cells like this one, Python code cells, or markdown code cells. So what you can do is switch the cell type to from one type to the next by first pressing Escape to be in command mode. And then if you press M on a cell, it will convert it into a text cell. So here it ignores that it's Python anymore and doesn't execute it anymore. It's just HTML text or markdown text. If you want to switch back to Python mode, you can press Escape to make sure that you're in blue mode, and then Y. Okay, and then you're back to Python. You can execute again. So in the text cell, you can also put images. So for instance, if you go before, like there is a big cell at the beginning, if you double click on it, you see that this is actually markdown with a mix of text, titles, and also this syntax to insert some images. So I don't want to modify it, but it's just if you get this representation, don't worry. You can just press Shift Enter and you go back to the HTML rendering of the markdown. So if you select the cell where we have executed the print statement, you see that there is a counter here that is incremented and that say that this is the third instruction that we have executed. If you press Control Enter instead of Shift Enter, it's going to execute this cell in place and not move the cursor around. So if I do that several times, you can see that this counter is incremented. You can also define a variable like a equal 1 here. Press Shift Enter. And then insert a new cell, a new Python cell. So here I'm on the here, and I would like to insert a cell here. If I press B, it's going to insert a cell below. In your opinion, what should I press to insert a cell above? A. So let's do A. And here, if I do print A to print the value of my variable here, you see that the two cells, they are related, they are running in the same environments. If I define a variable here, I can access the content of that variable in the next cell. So they are all running together, which means that we need to run the cell in order. Otherwise, we might access a variable that is undefined and get an exception message. For instance, if I press B and B has never been defined before, I get a name error, and it says B is not defined. When you get an error message in Python, it's very important to actually read the error message and not panic. And the part of the error message that is most important is generally at the bottom of the traceback. So I don't know why the rendering is weird here. But so usually you have this kind of traceback, and then the error message, and then maybe several steps, and finally the inner, the original problem. And so here it says exactly that B is not defined. So what we can do is define B equals 2, and now we don't have a message. So here we use print to see the value of B, but it's also possible to just put B at the end, and then we have out. The output is basically the last Python object in the cell. It's also printed by default. Okay. It's also interesting to know that you can delete a cell and move it around. For instance, you select the first cell here, you can press X and then V, and basically it's copy and paste. So you need to be in a cut and paste. You need to be in command mode to do that. So press Escape first, X, and then move somewhere else, and V to paste it. Okay. So if you press if you delete cell by mistake and you don't, and for instance you copy something else and you lose the ability to press V, you can also use the edit menu here, and you have undo delete cells that you can do repeated several times to get your cells back if you delete them by error. Okay. So I think that's it for the main keyboard shortcuts. Now we're going to talk a bit about NumPy. So NumPy is a baseline library, a building block library for the full SciPy ecosystem. So it gives you the ability to build numerical arrays and to do algebraic operations on those arrays, and linear algebra in particular. So for instance, we can use, so this is a convention to import NumPy as NP to have some kind of short alias for the NumPy library. And then we can do NP, some module or some function subclasses to use it. So for instance, if you want to use a function and you don't know what parameters that function take, you can put your cursor inside the function here and press Shift Tab. Actually, I need a comma here, and it doesn't work. Yeah, I need to import NumPy first. Then if I press Shift Tab here, you see that I have the documentation. If I press Shift Tab a second time, oops, or plus here, okay. That's weird. There's something weird on my machine. If you press plus here, you can see the full documentation of that function. And here there is a single parameter that is important, which is the seed. And it explains what it is. So, and also, for instance, if you don't remember the end of something, you can press a tab after the dot here, and it will give you the list of classes that are in that module, or the list of functions that are available in that module. So here I want to use random state, and then seed equals 1, 2, 3. Okay. So I will create a random state object and call it R&D in a variable, and then use that R&D variable, that random state object, to sample some data using the uniform distribution between 0 and 1. And I will generate an array with 2 axes. And the first axis has 3 dimensions, the second axis has 5 dimensions. And so then I can print my array. I can execute again. And so when you print a NumPy array, you see that it looks like a Python list that are nested and without the commas. It's just the string representation of the array. Alternatively, what we can do is just do that, put X here, and we see that it's an array. It's more explicit. And basically, we have values between 0 and 1. They're all positive. And you can see that we have 3 rows and 5 columns. So what the size here can be either an integer or a shape using a tuple. For instance, if we want more levels, we can have 3 axes. And here you can see that we have 3 nesting levels, 1, 2, 3. Okay. So I will come back to the original NumPy array. Something that is interesting also is that if you press A to have a new cell, all of the array have a shape. So the shape is the n-dimensional size of the array. So the number of rows, then the number of columns. And if you have 3D, then it's just axes in the right order. And also there is a data type. So if I press B, x.d type, and it's the type of the elements of the array. So here it's 64-bit floating point values, so decimal values. You can also have integers or Boolean variables and so on. Complex variable and different level of precision. So once we have an array, we can use this syntax to access a specific value. So because my array has 2 axes, I can access using an integer index the first row and the first column, and I will get this element at this location. I can check that 0.69 is this one. So if I change this, if I take 1 instead, I will get this one. No, this one. Okay. So here first is the lines and the rows, and then the columns. And also something that is very important to know is that in Python, when you index, it starts at 0. It's not like MATLAB or R that start at 1. In Python, it starts at 0. You can also get a full row instead of a single element of the row. So here we take the full second row. And this is actually a NumPy array. If I remove the print here, oops. You can see it's a NumPy array, and it's basically a slice of the previous array. It's also possible to slice a column by using this marker, the column marker. So here it means that basically we take all the rows that match the first column. This is some kind of wildcard. So if I do that, we take the first column. So we have 3 elements because there are three rows in the first column. If I go back here, we take those 3 values vertically. Here. So here it's also possible to use this notation to get the row by putting it explicitly like that. If you have a single integer, it's the first axis, but you can be more precise and slice this way also. This slice notation is actually a shortcut for 0 to -1, which means take everything. Not -1 actually, because the last one is is excluded otherwise. So you can actually put integers like 0 to 2, for instance, to slice a specific part, or 0 to 1 and so on, 1 to 2 and stuff like that. And you can use -1 if you want to, or -2 if you want to start counting from the end of the array. So when you just have the colon, it basically take everything. Otherwise, you can put integer before and after the colon for the beginning and the end. And the end is not included. All right. So this is like Python list slicing, but the difference with Python list is that we can have n dimensions, so we can take many slices and on different axes. There is this notion also of transposing an array. So this is the same array, but this time if you look at the shape, I know. I need to put it inside here. The 3 and the 5 have been switched, so we have now 5 columns, 5 rows and 3 columns, and basically we are just switching the two. So it's doing this operation, the transpose operation in mathematics. So instead of working with random data, we can also generate data that has some structure. So for instance, if we want to create a single 1D array with value between 0 and 12, and we want 5 values between 0 and 12 with a fixed interval, we can use that. So you see that the first one is 0, the last one is 12, and then we have 5 values and they are equally spaced. It's also possible to turn a one-dimensional array, which we generally treat as a vector, as a row vector, into a column vector by adding a new axis and taking the values as the column like this. So if we do this np new axis, basically it's some kind of marker that will reshape the data automatically to introduce a new axis in the array, and by default the value is 1. So we have one column like this. So it's a bit weird, but it's very useful because for machine learning in Scikit-Learn, the input features are always two-dimensional arrays. Even if you have a single feature, we will use that to put that as a column so that we know that the model knows that it's to be treated like a feature and not a single sample, basically. So we can also use that to generate the data again. And so as previously I've demonstrated that you can use shape to access the shape attribute. It's also possible to do a reshape, and as long as the new values match, the product of the new values might match the product of the old sizes, then you can reshape the array. But if you compare this to what we did with the transpose, so if I go back here you see transpose, the first is 0.69, then the second one is also 42.3, and then 0.28.6 here. So remember that pattern. If I go here, you see that they are not following the same pattern. Because basically here, when we reshape here, we are not transposing, we are just rearranging the data into a new structure, but the order has been preserved compared to all the values taken in the original order. So maybe it's a bit weird. I can give you another example. Press A. So if I do np.arrange, for instance, of 12. So this is just an integer array with values between 0 and 11. So 12 values that increment. So 12 is 3 times 4, for instance. So I can reshape this as 3 times 4. And basically I will have 3 rows and 4 columns. It's the same data, but arranged as a two-dimensional array. I can also arrange it as 4 rows with 3 columns. It's also possible to do that. And you see that the order is always the same. It starts 0, 1, 2, 3, 4, 5, 6, 7, 8. So reshaping is just creating a new view on the same data, but the internal ordering of the data stays the same. It's not a transposition operation. You see that the order is always the same. Okay. Finally, it's also possible to do what we call fancy indexing. So it's basically we use a NumPy array with integer values to index another array. So let me print x just before. So here we are going to use 310 to index on the columns. This is the second axis, so this is the columns. So we are going to take the column number 3, 0, 1, 2, 3. First, this column here, here. Then the column number 1, then the number column 0, in that order. And we are going to extract a copy of x with those columns and ignore the other columns. So you see, the first here is the third column here. It's the fourth column because we start at 0. It's column number 3 is taken as the first column in the output, and this column is taken as second column, and then the first column is taken as the third column here. Okay, and here we have 310 because we printed it here. Okay, maybe I can remove it. It's gonna be easier to see. Okay. Okay. So when we do that, we make a memory copy. When we do a reshape, it's just a new view on the same data. And here we are forced to make a memory copy because we are completely rearranging the data. You have questions on this? Yeah.
Why would you ever reshape your data? What are the applications?
Reshaping the data can be useful, for instance, if you have a three-dimensional array of images, a set of images, and each of the images have height and width as 3 different dimensions. Sometimes you want to access the pixel values as a vector, and you don't really care about the location of the pixels anymore. So if you have images of 8 by 8, if you have like 42 images, and they have, sorry, I should take this. So if you have an array, and there are gray level images, so there are no colors, you can have 42 images and a height of 8 pixels and a width of 8 pixels. You can also treat those as a 2-dimensional array with 64 pixel values for each of the images, and you don't care about the specific location. And for Scikit-Learn, most of the machine learning algorithm, they need this kind of 2D data structure. They cannot work naturally on images, for instance. So you need to find some 2D representation of the data, and the most natural way to do that would be to just to reshape. Sometimes it's a bad idea to do it, but it depends on the application. Yeah, so if you have the data stored like this, you can reshape it like this, and then you can pass that to matplotlib, and matplotlib will recognize that this is an image and make it possible to display it. There is another type of arrays. Yes? Sorry.
So you had to make a memory copy of that because you rearranged the array, but you didn't change X, did you?
No, yeah, X is still the same. If I execute this cell again, X is still the same. And if I modify, for instance, I can copy that into Y, store the result into a variable named Y. I will display Y here. I can change the values in Y. For instance, 0, 0 equals 0. I will display Y. So you see that now Y has a 0 here. If I look at X, there are no zeros anywhere. So X has not been modified. Because when you do fancy indexing, you're forced to make a copy, basically. Most of the time, NumPy will not make any copy when it's not necessary to avoid using too much memory. If you want to make a copy explicitly, it's possible to do, for instance, here. I can define a variable z, which is a copy of x. And then you can modify z without modifying x. So it's also possible to make a copy explicitly. Sometimes it's useful. when you do fancy indexing, it's making just a copy of the fragment of the data that is indexed. And otherwise, NumPy tries to not make any copy if it's not necessary. And when you reshape, it doesn't make a copy. If you slice also, previously we used the slice notation, for instance, here. Here, it's not a copy, it's just a view on the original data. So it's not allocating any new memory. So slicing, reshaping, they create views, and fancy indexing, that makes a copy. Okay. No more questions? Yes?
Is there any benefit to making indices and NumPy instead of a list? The list is the work as well.
So you could use a list of integer to do fancy indexing, and NumPy will basically convert the list into an array implicitly. So there is another data structure that is useful, especially for machine learning, which is called a sparse matrix. And NumPy does not support sparse arrays by default. Maybe that's going to change in the future, but so far it's not the case. So to have a sparse data structure for two-dimensional arrays, we can use SciPy sparse matrices. So a matrix is a two-dimensional array. There are NumPy matrices, but they are a bit weird, and they are not sparse anyway. So most of the time, I would advise you to not use the NumPy matrices, but just use the NumPy arrays. But for historical reasons, the sparse data structure in SciPy, they are only for two-dimensional arrays, and they are called matrices. So let's create a NumPy array with random values like we did previously. So this time we have 10 rows and 5 columns with values between 0 and 1. What we can do is use this notation here to put some zeros to the small values. So if the value in x is lower than 0.7, anywhere it's lower than 0.7, we will put a 0 in it. So if I do that, you see that only the big values have been kept, and all the others are replaced by a 0 value. If you do that, in NumPy, you will still store all the values that are 0. And that might be very costly on large data structures. So for instance, here the data size can do n bytes. It's 400 bytes, so it's very small. But we are storing all the 0 values in memory. To avoid this, what we can use is to import the sparse module from SciPy and to use the CSR, compressed sparse row matrix data structure from SciPy to convert the X array into a sparse matrix. And if we do that, if you print it using print, you see that basically internally what it does, it stores the locations of the non-zero values and their values. And so if you have very few non-zero values, it's much more efficient to just store the location of the values plus the value than just storing the values in a big memory chunk with the right locations. You can always convert a sparse matrix back to a NumPy array by using two-array. But be very careful if you do that, because whenever we use sparse matrices in Scikit-Learn for real applications, the array might not fit in memory. Even if the sparse matrix fits in memory, the NumPy array might not fit in memory. So you can do that on toy data set for debugging, but never do that on real data, because otherwise you will shut down your computer, basically. It will be very slow and then crash. Sometimes you get an error before, but it can be very problematic. So to create a sparse matrix, in real applications, you cannot create the NumPy array first because it's too big. So what we do is that we can use a lil matrix, list in list. And with this sparse data structure, it's possible to modify it, to add new elements like random values here in a loop very efficiently. So a lil matrix is very efficient to append new values in it. However, it's not very efficient to do a linear algebra operation on the lil matrix. So what we want to do most of the time, so you can convert it back to an array. If you need to do machine learning, for instance, on a Lille matrix, what you would do is convert it to a compressed parse row or a compressed parse column, CSC or CSR. And some algorithms, they are very efficient with CSR, and other columns, they work column-wise, like a random forest, for instance, and they would be much more efficient with CSC data structures. So we would use either Lille matrices or CO matrices, it's another kind of matrix, to create the data from reading some values from a file or a sensor or something like that, and append that in the data structure, and then convert it to a CSR or CSC to do the actual mathematical operation, linear algebra operation. So for sparse matrices, there are many representations, and there is each of them has trade-offs. The CSR and CSC, they are very efficient for linear algebra. Lille and CO, they are efficient for building the matrix from another representation. And diagonal is only for diagonal matrices, and I don't remember what are the trade-offs of the others. In practice, in Scikit-Learn, most of the models in Scikit-Learn, they are efficient if you have these representations. So finally, we also want to use matplotlib. So matplotlib is a graphical plotting library for data, typical NumPy arrays. So first, we connect matplotlib to the notebook so that when we use matplotlib, we will not create new windows to display the results, but it will include the result directly into the Jupyter notebook. So you can use matplotlib inline. Then there is a convention to import the pyplot submodule of matplotlib as PLT, which is basically the main entry point from an API point of view to define interactively a plot in a notebook. So you can use plt.plot that takes x value, x array, and a y value. So x is going to be values between 0 and 10 and 100 intermediate steps. And for each of those values, we will compute the sign function at each of those locations. And we get this. So this is the input, and this is the output of x and y here, basically. And so you see that it's very smooth because matplotlib is doing some kind of interpolation. But if I do less steps, you see that then we see the actual values. If I put many more, so it still works. Also, there is this specific semicolon here. If I remove it, you see this, which is ugly, because basically matplotlib PLT plot return a plot object, the lines to the object, in a list, and a Jupyter notebook will always print in the output section the last object that you have. So if you want to silence this, you can use the semicolon, and basically that will return none instead, and none is not displayed. It's just a trick to avoid this noisy output. Okay, so if you have data, you can also do a scatter plot. So here we have two arrays. They have the same size. And we will put on the x-axis the first array and the y-axis the second array. And then for each of those combinations, we will get a dot. And this is what we call a scatter plot. So those are Gaussian distributed values. They are sampled independently of one another. So you can treat the pair of the two values as a multivariate Gaussian with a spherical covariance matrix, if you like mathematics. This is a scatter plot. So the scatter plot is very useful to display data if you have two-dimensional data. You can also display histograms. For instance, if we just have x. Oops, sorry, I didn't mean to do that. So let's press B here, and I can do plt.hist of x, and maybe bins equals 50. So here you see that it outputs a ton of non-interesting stuff, and then the actual value, the actual graphical representation. So here we'll use a semicolon to get rid of that. And here you have a one-dimensional distribution of the data, empirical distribution of the data using a histogram. So typically we use histogram for one-dimensional data and scatterplot for two-dimensional data. And if you have n-dimensional data, you need some kind of dimensionality reduction to be able to do a scatterplot. Okay. Finally, it's also possible to use PLT imshow if you have two-dimensional data with the continuous values. So for instance, here we have x that vary between 1 and 12 and with many intermediate steps. We convert x into a column vector. And then if we do this kind of operation, NumPy will do what we call broadcasting and will generate a two-dimensional array. And the values of each of those locations is going to be dependent on x and y. And it's going to be a two-dimensional array. If I press this, you can see that it's a 100 by 100. And if I use imshow, I see the value using some color map, which is viridis by default. So basically, I think yellow is high and blue is very low. And it's also possible to use a contour plot to do the same kind of representation, but using lines. And there is a convention that 0 here is at the top left corner, where here it's at the bottom left corner. So it's a transposed representation, but it's basically the same kind of representation, but here you have continuous colors and here you have lines. It's also possible to do contour F, I guess, and to get this kind of representation, contour or contour F. Okay. Finally, matplotlib has also the ability to do some simple 3D plotting. It might be useful for impressing people on PowerPoint slides. In practice, I think it's useless, and this kind of 2D representation is better. You actually see the data better. If you really want to do 3D volumic representation, you might need other libraries like Mayavi, for instance. Okay, so I think that's it for this introduction to the tools that we're going to use for machine learning. These are the dependencies of Scikit-Learn, basically.
Okay, so now we'll switch to the third notebooks, and I think that then we'll have a break, probably. It's stopping at 10:30 until 10:30. So we'll stop probably around 10 for the break. So this one, again, recall a bit how we organize and represent our data. So, and we will go back to the first example, which is the Iris dataset, okay? So we already explained that each line will be a sample. So in this case, it will be a flower. And then for each of the line, we will get the feature. So for instance, the height of the petal, the width of the petal, and then the same for the sepal. So we'll have 150 lines, which will be, for instance, 150 flowers, and 4 features, which will be the feature that we extracted by hands that the biologist got. So the descriptions, we already saw the beautiful flower before. And we already saw how we were basically organizing our data. Yeah, the question is already the one that we said since half an hour. So how do you represent the data? What is ensample and features? I think that now we more or less know. So I will go directly on how do we basically load this dataset into Scikit-Learn. So this dataset is one of the Scikit-Learn which are embedded which is embedded inside Scikit-Learn, and we are using for benchmarking or training some algorithms. And this is based into this module which is a sklearn.datasets. And from that we have a load iris, which basically will return us the full dataset. So if we execute this part, and that we check, so iris will be basically a bunch, which is a dictionary kind of type of objects, and we can check the keys, and we'll see that basically we have the data that should correspond to our matrix X with, we'll see later how many features and how many samples. We'll have the target, which will be our classes. And then we'll have the target names, because in Scikit-Learn, we only handle numerical data, but in this case, we don't have numerical data. We have the name of flowers. So we have a connection between an integers and the flower's name. And then we have some extra things, which are the descriptions of the data sets. So seeing that we have like 0 data set, we want also to explain where they come from, what they contain, and extra informations. So the first thing that we can do is from the iris, we can get the data and check the size of the matrix. So if we execute this, then the first column, the number of rows will correspond to the number of samples, and the number of columns will correspond to the number of features. And what we can check is that we have 150 flowers with 4 different features, okay? And if we just display the first row, we obtain basically our 4 numbers, our 4 features, okay? Now we can also check what's the relationship between our data and our target. And we see that in the first case, we had 150 samples by 4 features. And in the second case, we have 1 class for each flowers. We can either print it, and we'll see that actually they are numerical data, and they are not the name of the flowers, and that's why we have a target name here, which will make the correspondences between 0 and the name of the flower if we want to have something nicer for the user if we want to display, okay?
So just a precision. So here you see we are using integers, not floating point values. So this is very, very important, because in Scikit-Learn, if we give as a target an integer, it's interpreted as a classification problem most of the time. And if it's a floating point value, it's a regression, a continuous variable problem.
Yeah. So
it's a convention. It's not always the case. Sometimes you can use integers for regression, but for classification, you cannot give floating point values. You should give integers as the target values. And what it means is that, if you can print the target again, is that, so here it's the first species, this is the second species, and this is the third species. And there is no meaning in the absolute values of those numbers. Like, it doesn't mean that this species is closer to this one than this one. You cannot compute the difference between the species by computing the difference of those numbers. They are just indicator values, categorical variables.
yeah, and we'll see later also that, this is something that you have to take care when you process categorical variables. So what we can do here is to try to find out how many of the first class do we have, of the class 0, how many of the flower of the class 1 do we have, by using bin counts. So we can use NumPy and call bin counts. And then we'll see that we will have 50 zeros, 51, and 52. Okay, so we have a balanced data set in the way that we have the same number for each species, okay? So do you have any question on that? Yeah? Okay. So here, so is what I was explaining. The class 0 will actually correspond to the setosa, the 1 to the versicolors, and the 2 to the virginica. And how can we find this relationship is by printing the target names. And now we can find the relationship, okay? So the first thing that we can do is to plot the distributions of one of the feature. So for instance, we selected the petal width, okay, which is a feature which is here. We took the feature number 3, okay, so we took only the third column. And then we just took took the third column, and then we plot the histogram for each classes. So we took the setosa, and we plot the histogram, which is in blue. We took then the versicolors, which is orange, and then we plot for the green one. So by just looking at this, we can already investigate, for instance, if we can easily distinguish one class compared to others, okay? In the same way, already Olivier spoke about this histogram, and then he was also speaking about the scatter plot, where we can actually visualize 2D. So we can go even a bit further by not only plotting one single feature, but two features, okay? So to do that, we can put a feature on the x-axis, a feature on the y-axis, and do the same scatter plotting. And in that case, for instance, we selected, so for the y-axis, we took the first features. For the x-axis, we took the last features. So it's better to name them. So we took the sepal length for the y-axis and the petal width for the second axis. And then we plotted each individual features values, okay?
So can you show how we get the feature names in the code?
Yeah, so the features names is, it's here. So we get the index zeros, and then we take the list which contains the feature names, and we take the corresponding name, okay? And then we get our plots. So for instance, here we can already find out that using only these two features, we will be able, with a symbol line, to precisely classify the blue, which is the setosa flowers compared to others. And here it will be a bit more noisy to make the selection, okay? So just by visual clue. So now the exercise is just to play around with, you can play around with the index of x and y, and to see which representations is actually the best one to try to distinguish the three classes. Okay? So here what we are trying to do is to go from 4 dimensions to actually 2 dimensions to try to simplify our problem. So is what we say here. So that's a kind of exercise of dimension reductions already. So we already spoke about it. Here we do it by hand, and then we'll see other techniques to do that. So you can try to play around and find the best combination of those.
So the goal is to find a graphical representation when you can draw a straight line that will perfectly separate the different groups. Here we cannot draw a line to separate the versicolor from the virginica, but you can see that it's very easy just using the petal widths to separate the setosa from the two others. So let's try a good representation. What did you say? 2 and 2. 2 and 2, but maybe one feature is enough. But actually, there is probably some overlap. So what we could do is, yeah, there is some overlap here. You see. So it's actually we cannot see it, but there are some bad classifications here.
Because you plotted one point over another point, so you don't see it.
Okay, so no perfect classification. It's actually, maybe it's not possible to find only 2 features to completely separate the species, and you actually need the 4 features, and we cannot just represent them in 2 dimensions. So. But you can see that there are some combinations that are better than others.
Okay. So do you have any question on generic stuff? No? Okay. So one of the scatter plot which you can use to see those interactions is actually in pandas. So it's a side of Scikit-Learn, but basically they have this scatter matrix where you can create a data frame, putting the data and the accounting. To have the name of the features, you give the feature names, and then you can plot these matrices, which I think we'll use Seaborn probably on the hood, and we'll show you basically all the interaction of what we're trying by hand now. So that's the univariate histogram. Okay, so it's like the histogram of the first feature, the histogram of the second feature, third and fourth. And then here, this is a scatter plot that we are doing. So the first column with the second features, etc., etc. So only by looking at this one, is what we're trying by just moving the indexes. So if you have a reasonable number of features, not so much data, because then after that you just see like a cloud of points, you can maybe look at those type of visualizations that can be helpful, okay? So what do we have else in Scikit-Learn to actually play with data? So we have three type of things. So we saw right now the load function. So usually we have a couple of very small data sets which are embedded inside the package, and you can use, and they start with load. While we have much bigger data sets that you can, which are, for instance, much more time consuming and used for benchmark, which are with fetch. So we'll first need to fetch the data from internet. They are not included inside the package. And then the last one is simulated data. So we generate the data. And usually they start with the make. So for instance, make blobs and stuff like that, or make classifications. So as explained here, you can already try by yourself so you can import from Scikit-Learn import datasets, and then use the auto-completions to see what you have. So dataset dot load, and then we'll see that we have different things. So we have things specifically for regressions or for classifications, and like this you can play with some models and understand how this is working or the specificities, okay? And the same, you can check the fetch, and you will see a couple of those one will need to be downloaded, okay? Yeah, so be careful because some of the data sets are kind of large, and if you might need like 200 megabytes just to download it. And if you work with text, the fetch news groups are, for instance, already the fetch news group is quite large, and that's why we propose some already pre-processed data sometimes. So you have to check the documentation to know which one are the pre-processed if you want only to work on the second part and the classifications. So right now what we'll do is that we'll...
Just a note. So all those data sets, they are only provided for debugging machine learning algorithms, like to try and evaluate a machine learning algorithm on some standard data set that are used in the literature, so that you can compare, that you can reproduce the results by comparing the accuracy on some standard data set. Most of the time you want to work on your own personal data, and in that case those are useless. You don't need to fetch anything. There is only one function that might be interesting. For instance, datasets.load SVMLite. Load SVMLite file. So this SVMLite file format is used by some people to pass around some data as a text file format. And this is a parser for that file format that can be used in the machine learning community. So it can be used on your own data. But for most of other applications, typically what you would do is find a way to query your database using a SQL connector, like a SQL Alchemy, for instance. Run a query, extract the data, convert it into a NumPy array the way you want. Or maybe extract that as a CSV file and use pandas to read the CSV and convert it into a NumPy array, or pass the data frame directly to Scikit-Learn.
And you have load files also, which does something like...
yeah.
You can...
And so my point is that if you want to work on your own data, you just need to find a way to load your data into a NumPy array or a pandas data frame, and that's it. You don't need to use any of this. You don't need the bench object or whatever. You just need an X and a Y that are NumPy arrays or data frames.
Okay. So now we'll work with a second data set to see. So this one will be interesting because it's about images. So we have the problem that Olivier mentioned here with vectors and how do we handle images when we want to make classifications. And this is called digits. So it's a smaller data set than MNIST, I think. And it corresponds to actually numbers written by hands of size 8 by 8 pixels. And the task will be to classify a handwritten image to find the number which is written on it, okay? So here the data set is lost digits, so we can load it exactly the same way that we did for the iris data sets. And then we can check what are the keys, and we have exactly the same like information inside, so data, targets, the target name. And we have an additional one, which is images. And this is because data will be the vectorized versions. So we have 1 line per image and 64 features, while that images will be number by image, by the height, by the width. Okay, so if we take the first image, then we can already plot the image or show the image. So if we show the data, so we have 1,797 images with 64 features. And if we plot the first line, we see that we have integer between 0 and 16. Okay, and that the target is corresponding to a number between 0 and 9. Okay. So here is what I was explaining. So that's the difference between the data and the images. So one is the vectorized versions, and the other one is actually the real images. So if I take the first sample here, if I slice over the first dimension, I will get an 8 by 8 matrix, which represent an image. So, and how to get from one to another? So it was the trick of the reshaping, so that you can use a reshape, and then you can get from data to images or from images to data. Okay. So now the more interesting things is to actually plot those data. So here we will try to plot each image. So if we check, we have EM show, okay, and we'll get an image, so which corresponds to an index. So here the index is 64. So basically we have a matrix here of 8 image by 8 image, and we will just show the image which is between 0 and the 64th image. And then we will just have a column map in grayscale, okay, and with interpolations, just to show. And then we will add a text on the bottom left, which will correspond to the target. So what you see here is actually the real data, and here this is the target, which is associated, okay? So that's just to show.
You can see that for this is very low resolution images, 8 by 8 pixels, and for instance, this one is kind of hard to tell. So you can expect that even if even human beings have trouble like classifying this one or this one, maybe the model won't be able to make perfect classification either. So.
Okay, so now the exercise will be to try to load another data set which is about faces, okay? So it's used for either face recognitions, I think, and basically do the exercise by loading the data and so you will need to plotting it basically. So you have a couple of minutes to play around, load the data, fetch the data. So it's a small package, so it's 1.5 megabytes, so it should be okay. And then just plot using EM show or with another column map. So similarly to what we did before. Okay. do you have any question in the meanwhile?
Having some issues loading SciPy data sets.
I will go and check.
Okay, so some of you had problems downloading this. You had SSL errors or stuff like that. It might be because you have a HTTP proxy on your corporate laptops, and you need to set up an environment variable, which is kind of complicated to get right. So for this exercise, just follow on the screen. But for the next ones, we will need to have to make sure that you could execute the Python fetch data.py stuff. So if you haven't, and you cannot do because of proxy configuration issues, use a USB key and try to download the notebook/dataset subfolder and unzip it in the right location on your own folder. So it's under notebooks/dataset. Okay. From someone else.
Okay. So before to check the solution, anybody have any question on what they try or no? Okay. So small tips because we didn't see up to now. So when you have a solution, usually in notebooks, you have something that say like a comments and then %load. And this is actually loading the content of the file which is in that locations, okay, in the notebook. So for us, it's kind of practical because we can load the solutions and directly play it, okay? So, so for you, is like if you don't know what this line was meaning, that's the meaning. You can just uncomment it, and it will load the solutions, okay? So basically, the code is really similar than before. We have the only difference is that we use the fetch Olivity faces. So here you can see I already downloaded it once, so I didn't have on the computers. So the first time that you execute it, if it's working, it will download the data sets into, so here into a generic folder, which is in Scikit-Learn data in basically the users folder, okay, because this is the default locations. So now if I'm re-executing again, it will not re-download the data because the data already cached, okay? So that's why you don't like re-download always the things. Then the rest of the code is more or less exactly the same than before. So we have faces, which is something which is, if we check the keys, will be equivalent to the previous thing that we had before. So we have the data, we have the images, and we have the target. Okay, so we don't have feature name or target name because here it was not meaningful. And then we just create figures of a given size, so 6 by 6 inch. And then we will just make subplots. And then we will take the 64 first image, okay, of the data sets, which we will index here. Okay, so we'll make a loop over the 64 first and just show an image every time on a grid of 8 by 8. And then we apply a bone color map, which is not a grayscale. I mean, it's kind of a grayscale color map there. And then we put an interpolations if the plot is bigger than the size of the image. So do you have any question on those, or you succeeded? So of course here you could plot random images if you actually, instead of creating I between 0 and 64, you could check randomly images that could be between 0 and the number of image, and if you wish to see some other things, okay? Okay, so that's all for this notebook. That's how basically we load data. So now we'll pass to the notebook on the training and testing data, which is the 4th notebooks. Okay. So I will already set up matplotlib and NumPy, which is the first tell. Don't forget to execute it. After that, it doesn't work. So when we do machine learning, we already saw that we have two phases. So we call it like you have a phase where you learn the models and a phase where you want to see if your model is generalizing on new data. So that's the testing phase, basically. And if you want to simulate, because basically what you do is that you will have a data sets where you know everything, but if you want to simulate the case that you have a production system, you have to simulate the phase that basically you don't know anything about your target. So I should have, at the training, I should have all the information, data plus target. And then when I want to evaluate my models to know how good my model is, I will just need my data, but don't give any information about the target. So the training, what we will see here is how to basically split data such that we do properly these two, we split the data into categories, okay? One for the trainings over one for the evaluations. So we'll reuse the iris datasets, okay? So we already saw before that we can use the data, which we will call X, and the target that we'll call Y. So if you check the documentations, X and Y are recalled a lot of time in different algorithms. So X, usually we always refer to data, Y always refer to targets, okay? That's kind of conventions. So we can load the data, and now we can plot basically the targets, and we'll get our array that we already saw before with 50, 0, 51, and 52. So if you would like, for instance, you say, okay, I don't need Scikit-Learn to basically split my data into training and testing. I can just slice a portion of my data for my training using slicing with NumPy. The problem is that if you are not careful and that you forget to take care or to look at your data, you might have only the zeros into your training and do not shuffle your data. And that's basically what the tools of Scikit-Learn allow you to do. They allow you to do a proper splitting, okay, without taking care about those things. So the first function that helps you for that is the train test split. And this is in the model selections modules. So the idea is that you import this function, okay? And then you will give your X data, your Y data, and then you will say the proportion of training samples that you want, and then the proportion of testing samples that you want. So here we want half of the data that will go for the training and half of the data that will be in the testing. And then here we set the random state, which is the seed, which will first shuffle the data. Okay, so we'll first shuffle the data and then split half and half. Okay? Yeah.
Does that have to equal 1 when you add those two?
Sorry?
Does that
I'm.
No, actually, this makes it possible to subsample, so it cannot be larger than 1, because otherwise you would have an overlap between train and test. But you can also put integers if you want to have a small training set of just 20 elements. For instance, you can put train size equal 20. If it's lower than 1, it's treated as a fraction. If it's larger than 1, it's treated as an absolute number of samples. But the two together, they have to be less than 100%. And it will make sure that there is no overlap between train and test. And if you don't, you can omit train size and just give test size. And in that case, it gives you the complement for the training set.
Question.
Yep.
So yesterday during our TensorFlow session, we split our data in 3 ways: test, validate, train, validate, and test. Do we also use similar approach when we work with classic ML algorithms?
Yes. So what you could do is use train test split several times. Once to split what we call the development set and the evaluation set, and then so where is it? So you can have a full data set where you have everything, and then you can split some, do a first train test split to keep something for the final evaluation, and we call it, to make it more explicit, we can call it final eval, and this we can call it development set. And inside this, you can split again a train and a validation set, for instance, or a test set. It's just that we can do that several times, look at the value of the model on the validation set, tweak the model again, reevaluate the model with the new hyperparameters, and do that several times. And at the end, once we have found the best model, we can finally evaluate it on some things that we have never seen before. The thing is that if you evaluate a model and change something, you cannot reevaluate with the same validation set or test set because you used it. You can only use it once for the final evaluation. So we will see also this afternoon that you can do cross-validation instead of a single train validation split. When you do deep learning with TensorFlow and stuff like that, training a model is so costly that you cannot use cross-validation because it's too compute intensive. And so you do a single trace validation split instead of using cross-validation. But it's basically the same. Here we could use cross-validation here and use a final evaluation set for the final evaluation.
Okay, so here I will go back to okay, no battery. Anyway, so to half and half, and then we can observe all the data that have been selected. So we'll just check the train Y. Okay, so here it's returned 4 variables. So the training X, so the training data, then the testing data, and then the training target, and then the testing target. And now we can basically plot, for instance, the training Y, and we'll see that our labels, just to verify that we had a shuffling, our labels have been shuffled previous to basically make the split. Okay, so that's why it's more powerful than just using NumPy because we took care about the shuffling.
To rephrase this is that if we just use NumPy to slice in the middle, you would have 0 and 1s in the training set and 1s and 2s in the test set. And we would not be able to predict any 2s because in the training set we have never seen 2s.
So basically, you will have this in your training, and your testing will be something like this. So here you will never train on 2, and here you will you will test on 2 that you never saw before, and vice versa.
So okay. Yeah, if you want to be able to predict 2s, you need to have seen a couple of examples of the class number 2 in the training set. Otherwise, the model will never think about trying to predict 2. So this is why we need to do some random permutation before doing the train test split.
So here we printed the train labels, and then we see that we have also shuffled the testing labels. So we have a kind of tip, which is stratifying. So stratifying means that when we make the split here, we didn't care about the proportion of each class when we make the split. So for instance, we said that we have 50 label of each classes at the beginning. So when we make the split, we didn't take care about the proportion that we have in the training and testing if they are equal, because naturally they were equal, afterwards they might not be because of random sampling. So we can first check what was the proportions. So for instance here, that's the full data set. So we saw that we have 50 examples in each, which represent about 33.3%. Of the class 0 and the second class and the third class. So this is highly balanced. I mean, this is completely balanced. And one that we make our splitting here and that we change the same proportion, we see that we have 30% of the first class, 40 of the second one, and 30 of the third one. So on the training set, we imbalanced our data and having more, basically, of the second class. And it also have an impact on the testing because this is a complementary in that case. So we have less of the second class. So it should be, I mean, if we want to conserve basically the proportions in training and testing, I mean, the same way that we have in the original data, we can pass a parameters, which is called stratify, and we can give him the target, and it will take care about splitting to have as much as possible the same proportions, okay? So if we repeat this, and now we can see that the proportion of all the classes in that case have been respecting in the training and the testing class, okay? Yep.
What if you have a severe class imbalance, like very small samples?
Then you might have the corner case where, I mean, if you have one samples, I'm not exactly sure it will fail or not.
So if you have a one class that, for instance, has a single sample, then I think it will be automatically be put in the training set. But honestly, doing machine learning with a single example is useless. So, but if you have an imbalanced data set, it will preserve the imbalance. If you have in the full data set, if you have like 80% of the first class and 10 and 10, for instance, if we try to preserve as much as possible 80, 10 and 10, 80, 10 and 10 everywhere.
And so and basically that's the best because in the real life, if this is because of real life, you will exactly get this when you want to train your models. So you need to preserve that in your training and the testing. And then you have to be sure to use good metric when you evaluate your models, to be sure that basically you will not see wrong. I mean, you will not fool yourself.
Yeah, you want basically the class proportion in the test set to be the same as the real class proportion. Otherwise, you cannot interpret the accuracy that you get on the test set if the class proportion does not reflect the actual distribution.
Okay, so now we'll train our first models on those data. So we'll use k-nearest neighbors. So it's a classifier that will check the neighbors. So at a sample, we check the samples around him to know which class he is, okay? So here, as Olivier already presented at all the beginning, we will use the fit and predict functions. So fit will make the training. And so what we do is that we create an instance of a k-nearest neighbors. We fit only on the training part of the data. And then we will predict only on the test parts. And in that case, you can see that we never used test y at any points, okay, apart of afterwards when we make the evaluations, okay? So we train, we predict, and then here we will check basically the accuracy. So how many times the testing and the prediction agree together, and we make the sum and we divide by the length of y, and it tells us that we have 96% of right answers, okay? So it's a fraction of correct answer. And this score is called, I mean, that's the accuracy, basically. So now we can even try to go a bit more in depth by just checking which of the labels have been correctly classified. So we can use numpy.where, and we say, okay, when predict y is equal, so agree with the test y. And it will give us a list of the indices of the that are well classified, and we can do the same with the indices which are not correctly classified. So in that case, we have 3 samples which are not well classified. And as we did before, we could make a 2D scatter plots and choose 2 axes where we want us to visualize the data and check which one of those, for instance, have not been classified. compared to others. So for instance, here we plot our first class, which is the green class, or that's the third one, but the three classes of the flower. And then in red, we classified basically the misclassified samples. So now there's an exercise on basically plotting, finding the labels of those samples and modify basically this scatter plot. Yeah, you have the question before.
Is it generally the case when it's more difficult for us to characterize samples that are on the interface between two clusters?
Yeah, in that case, yes. In that case, it will be more linked to the neighbors. But basically, that will be the exercise of trying to understand why those samples are misclassified. So
keep in mind that here we are doing a 2D representation of a 4-dimensional space. So it might be the case that the clusters are well separated in 4D, in high dimension. But when we project only on 2 axes, we have some overlap. But maybe in the full data set, it's not the case. Here, apparently, it's also the case, otherwise k-nearest neighbors would not make any mistake. So
Why is it 4D?
it's 4D because we have sepal heights and widths and petal heights and widths and centimeters.
okay, so yeah, here the exercise is to basically understand why those 3 samples are misclassified. And then is also a bit of plotting by just giving, so classifying and giving the index of those 3 points in the scatter plots. Okay.
So basically, if you read the instructions, you can set different markers. So in matplotlib, when you do a scatter plot, there is a marker keyword argument in the scatter plot function. And you can give, if you look at the documentation of matplotlib by using a shift tab or going to the matplotlib website, you can see that you can give different markers for the different points and use the matplotlib legend to be able to see the different markers, what they mean, and what is the true class and what is the for each of the errors.
Yeah, so here, for instance, what would be interesting is to know which class it should be and in which class we classify to understand why is it that colors or why is it misclassified.
If you don't want to do it with matplotlib, what you can also do is for each of those data points that you identified previously, if you can scroll up. So here you have the indices. Okay. Here you have the indices of the 3 data points. You can just print the petal lengths and sepal widths to see which is which and print the class for each of them and see why it made a mistake. Try to understand why it made a mistake.
So as before, when you think that you have found why, you can put the stickers, and like this we can move forward afterwards. Okay, so by just looking at the data without any plotting, we can already check. So we already say before the incorrect indexes. So is this variable that was defined here. So NP where prediction are different from the test Y, and then we're getting 4 indexes. Okay, so I just print here those 4 indexes. And we can already check what was the class in the test Y and what is the class that we actually predicted. So in that case, we predicted 2 and 2 for the first one, and class 1 in that case, and then the one we swap, we predicted 1 and it should be 2. So to find out which sample are which one, we can select the data. And basically, we took the feature 1 and 2 because they are the feature which we are plotting here. So here, in X, we plotted the second column, and in Y, the third column. So here we are just getting the second and third column, and we take the value of that correspond to the incorrect samples. So if we check just for the last one, which is it's the only one that we swap from 1 to 2. So he's at position 2545, and if we check this one, is this sample which is here. So what we said is that we predicting class 1. Class 1 should be this class. Okay, so we predicting orange, and it was actually a green. Okay, and those one have been predicting green, and they were class orange. So the feeling behind it, because what the nearest neighbor is doing is checking in that case, by default, we check the 5 nearest neighbors. So we check the 5 nearest neighbors around that point. And of course, there is more orange than green. So the classification will predict as an orange point, but the truth was that it was a green one. Similarly, for those one, we checked that the 5 nearest neighbors that were the closest to those points were green. So we classify as green, but actually it was some orange one. Okay. So the reason is because our heuristic that to check like the 5 closest didn't work for those 3 specific samples. Okay. So I can load the plotting. So this is just repeating what we did before, but in a nice way. Okay. And now we just we just express the same thing than what we saw.
So if maybe, okay, maybe you can show the matplotlib. Here we are using specific markers here, X, S, and V. V is the triangle that goes to the bottom. S is square, and X is the cross. And you see that we are passing the marker for each of the incorrect indices, and we pass the label also as I as the label, so the index, and so this makes it possible to have this that has been displayed here automatically as the legend. Okay. So this is matplotlib stuff, and so can you display this? Okay. So you see that here we have a gray point that is in the middle of the a gray point that is in the middle of the green one, and here another green one that is in the middle of the gray point, and stuff like that. So, in your opinion, how we could fix the model here to make it avoid those kind of mistakes? Remove outliers, but those are not outliers; they are real data. They are not significant outliers. They are in the middle of the high density region of the data, and they are not mistakes. They are. I don't know. I'm not a biologist, but let's assume that the biologist did not make any mistake in labeling the training set.
Project otherwise?
We could project otherwise, but this is for visualization, and the k-nearest neighbors classifier has actually used the whole 4 dimensions. It didn't use just those 2. It used the 4 dimensions. It's just that we can see the problem with those 2 dimensions is enough that we can see the problem, but the model has used the 4 dimensions.
Could you alter the split of the classes in your training set so it's weighted a little bit more heavily towards the misclassified samples, or try maybe making synthetic data?
I think it's good to have the split that preserves the natural balance of the data, and here they are naturally well balanced. I'm not sure it's representative of the true distribution in nature, but changing that is not likely to it's just the class 2 and 1 and 2 that are being mislabeled, so I'm not sure we can reweight those to fix that issue. So first, what we could do is maybe focus on a larger region, so larger number of neighbors, like change the value of k in k nearest neighbors classification. But for this case, I'm not sure it's going to fix it. Maybe it's just fundamentally the features that we use are not enough. So maybe in this case, the only way to fix it might be to collect additional features like the colors or information on specific patterns that you could see on the flowers or stuff like that. Or if you can do a biopsy and do a genetic analysis, that might be an even better feature. And you could use that as additional feature. Sometimes the data itself is what is limiting the model, and it's not actually a choice in the model. Another way that we could do is maybe the metric space that we are using is not good. Maybe we should rescale like maybe divide by the standard deviation of the distribution, and maybe in that new space, the metric space would naturally split the data more. I'm not sure it's going to work in this case. It's quite unlikely, but there might be some alternative metric space where it's the classes are better separated. Like the centimeter space has no guarantee to be the best space. There was a question about? No? Yes? Mm-hmm. Maybe the data in the boundary is different from what?
Apply a different criterion.
Yeah, we could also try another model, like a random forest or something else. But because there is this overlap in that region, it's quite likely that any other model will fail in a similar manner.
Yeah, probably when you will focus on those samples and you misclassify some others because now you look at this specifically.
Okay.
Okay.
Okay. So changing the neighbors to a larger number of a larger neighborhood might remove some of the classifications error, the mistakes. However, be careful that we have a very small number of test samples, so maybe it's just by chance that it's working better. But indeed, that might improve a bit.
And we'll try to play with that in the next notebook, actually. Okay. So do you have any other question about training, splitting, and... It's fine? Okay. So next one will be about supervised learning, and specifically about the problem of classifications. So up to now, classification is what we did. Okay, so our target is a category. We have a defined number of categories, and we try to predict a category. So no continuous variables. So here we'll look at basically two models. One which will be the k-nearest neighbors, and the one that will be linear classifiers. I don't remember if it's a SVM or logistic regressions, and see a bit like how those things are working. So first cells to import matplotlib and NumPy. So now what we'll do is that we'll create a synthetic data set. Okay, so we play up to now with iris. So now we'll just make our own data, which is called make blobs. So it's make blobs. We can tell how many blobs do we want in our data sets. We can set our random states, and then we can also explain basically what's the standard deviation of those blobs. So by executing this, we get a X which contain 100 samples with 2 features, and the Y which is also 100 samples. Okay, we can plot the 5 first features as we already did before with the associated classes, and we can make, because we have 2 dimensions, we can plot also what our data look like. So if we do that, we get that's the data set that we just generated. So 2 classes, 0 and 1, and they are blobs because they are basically Gaussian distributions, okay? And they are like 2 circles. So they have the same standard deviations in both. Both circles have the same standard deviations.
And so you see in this case that the standard deviation is so large that there is a significant overlap So we cannot expect by using just those two features to get a perfect perfect classification accuracy. Actually, for this specific data, if you know that the true distribution is two blobs that are Gaussian distributed with the same standard deviation and spherical covariance, what is the best model that you can? What is the perfect classification model? It's not perfect, but what is the best model that you can make? Do you have an idea? A Gaussian model, but what do you mean? How would the decision boundary look like?
Not a straight line.
A straight line?
No, not a straight line.
Not a straight line. A quadratic line. Actually, it is a straight line, the best boundary that you can make. So if you know the true parameters of the true distribution, it's going to be the centers of the Gaussians. So you will have two centers, one approximately here and another one here. What you could do is take the line that goes through those two centers and in the middle draw the perpendicular line, and that would be the best decision boundary that you could get. It would not be perfect. There would be some bad classification on each side. But this would be the best classification model, and it would be a linear model. It would be a linear decision boundary. However, we don't know the true position of the samples. We don't know the true parameters of the distribution. So we have to find a model that is just using those samples, those data points that have been sampled from the distribution, and using those finite data points that we have. What is the best classification model that we can train, and we don't know ahead of time that those two classes are Gaussian distributed, so we don't even know that the best decision boundary is a straight line. It's not just using those data points, it's not easy to see that it's a straight line.
Okay. Any questions about that? Okay. So how we did before? We saw that it was important to make a training and a testing split. So we just do exactly the same. And we will use 25%, 25% for the testing and 75% for the training. And we apply stratifications to stratify the data, okay? Just to not have any issues with that. So we got our data in X-train, X-test, Y-train, and Y-test, okay, as before. And is to recall basically the API. So we will call our fit to run our models, and then we will be able to predict using, to evaluate the generalization of our models using predict, okay? And then we'll use an evaluations to see if our predictions are the same than the testing, okay? So we already saw a bit about that. So what we'll do here is to use linear models, which is a logistic regressions, which is probably the most basic models, but kind of powerful. And we'll create an instance with the default parameters, okay? So if you want to know a bit more about the parameters, they are all here. But for the moment, we'll just focus on using the default one. So we create our models, and then we can check the shape of our data to be sure that we are properly splitted our data. So we will have 75 samples with 2 features and the corresponding predictions. And the first thing that we do is that we fit. So we learn our models on those data. So one that we learn our models, here we see that the output is also a model. So fit return the model itself. So it's allowing to do something, for instance, .fit, .predict, we could do that, okay? It's allowing to chain functions. That's why we have these outputs. So we can learn our model, and one that we learn our models, we can make the predictions as we did before on the testing data, okay? So here we have X test. We don't know anything about Y test. We get our predictions, and now we can print basically the predictions and the testing, And we see that we have misclassifications and some others that agree together. And the same way that we did before, we can compute the ratio of good predictions when the prediction agree with the ground truth. And here we obtain an accuracy of 72%. Okay.
Just can you please insert a new cell, not just there,
Yep.
just above this one, to display the value of prediction equal X test?
So that will return a Boolean mask. Okay.
So those are value true and false whether or not they agree. And basically what we want, the accuracy, is the proportion of true in that mask. And so when you compute NP mean, it's the average, NumPy mean. And basically you can treat false as 0 and true as 1. And it's going to just count the number of ones and divide by the total number of elements. This works because Boolean values are integers, basically.
So Scikit-Learn propose, the classifier, and regressor later we'll see, you have fit, predict, and you have 1 over helper function, which is called score, a method more. And this allow us to just output a specific score, which is actually for the classifier will be this accuracy. And in that case, we can give already the data and what should be basically the ground truth. And it will automatically compute the accuracy under the hood and give us basically the score directly, okay? So we don't have to make predict and then make the checking. We can already use .score and it will return us this. However, be aware that for classifier, it will be the accuracy. So if you have imbalanced data set that you do .score, it will return you the score using the accuracy, which is not a good metric in that cases. So you might want to use some other metrics.
Can you give, do you have an idea why the accuracy is not a good classification metric for imbalanced data? So imbalanced data is when you have, for instance, 95% of samples that are of class spam, not spam, for instance, and 5% of the samples that are spam, for instance. So.
Well, I think if you had a classifier that just said everything is not spam, it would be perfect or pretty close, 95% accuracy, but also useless.
Yes, exactly.
Yes. So I repeat so that it's recorded on the video. If you have a classifier that predict always constantly the majority class, like not spam, it will already have an accuracy of 95% accuracy, which is not very informative. It's misleading because you might think that it's a high accuracy classifier, but it's just a baseline that is predicting a constant target variable. So in that case, we could use alternative metrics, such as
balanced accuracy, for instance.
Balanced accuracy, ROC AUC, or F1 score. They are all in Scikit-Learn, and you can read the documentation if you
and
want to.
we'll focus on that this afternoon. There's something about the metrics. So we can also maybe try to understand if our classifier was already classifying goods on the training set, because it was the logistic regression doesn't have to learn boundaries, but it can already make mistake, and we can check like this if it's able to generalize well or not. So for instance, we are making an errors of an accuracy of 0.9, and then we drop to 0.72, so we were not good enough to generalize here. So because we have only 2 dimensions, we can visualize with a scatter plot. And plot basically the decision boundary of our classifier. So here we have our first class, second class, and we see that the logistic regression just try to find the line that best split the 2 blobs. And then we see that because the 2 blob overlaps, then we have some points which are misclassified on each side of the lines.
Maybe you could insert a new cell and use the double question marks to display the source code of the plot 2D separator function. So if you have Here we give you a way to directly plot the decision boundary, but it's no magic. If you want to know how it works under the hood, you can use a double question mark, and you see the source code. And in particular, what we can see, I'm looking for the coefficients of the model. Decision function. Okay.
So here we just make we call it the decision function of a mesh grid.
Yeah, this is what I would not have implemented this way. Okay. Anyway, what is in? Maybe you can stop this.
Remove it.
Close it. What is important for this model? It's a linear model, and if you introspect the attribute which is called coef on the classifier, .coef, so you see that you have this coef underscore. The underscore means that it's an attribute that is derived from the data, and there is also an intercept underscore attribute, and basically this is a weight parameter for the first feature, and this is the weight parameter for the second feature, and basically those two plus this one give you the parameter for the affine function that is the straight line in that two-dimensional space. So you can derive the equation for that line from those three parameters that were found directly from the data.
Okay, they were just afterwards. Okay. So it's fine? Yep. Okay. So how we saw before, you can use another type of classifier. So the first one has the assumption that you can find a linear separation between the two classes. Okay. So you try to find the coefficient that best splits the two classes. In the other case, you can use, for instance, the class nearest neighbors, which will make not such an assumption. What you will base his decision is on his neighbors. So it's a non-parametric approach with parameters. So we can import the nearest neighbors. And here, maybe 30 is a bit too much. One, okay, let's try the minimum one. So we'll just look at the closest samples to take our decisions. So we see that here we call the same fit and the same predict functions to do our testing and plotting. So here we are fitting our classifiers, and now we make the scatter plots only on the training data. Okay, and that's our decision boundaries here. Okay, so we have like a straight line here because we don't have samples next to each other, and then here we see that our decisions really rely on the sample next. So we have a very weird decision boundaries which try to isolate every sample, and that because the sample is alone, it will just focus on these samples. And
so maybe before going further, try on your laptop to change that parameter to higher values and see what it does. N neighbors to maybe 30, for instance. Okay. So this is with n neighbors equals 5, you get this. It's weird because it's disconnected decision boundary. Maybe 30 again. And so if you use 30, you see that it's going, the decision boundary is getting smoother, and it looks like a straight line, actually. So in that case, it's going towards the optimal model. It's not a guarantee, but in that case, a higher value of n neighbors is better.
So when you have a small numbers of neighbors, you will really focus on all the samples next to you and having like a
very local decision boundary,
which might lead to what we call overfitting. Okay, and when you want to avoid these things and regularize somehow, you will get larger numbers. And then you get such model like now.
So yeah, the fact that we have this overlap is caused by the noise. That is just the fact that the two distributions are very have a scale that is very large and overlapping. And so if you just make the k-nearest neighbors decision boundary focus on local features by using n neighbors equals 1, then you will basically memorize all the noise from the training set, and this noise does not generalize to the test set. So if you're too local, it's a bad idea, and you're memorizing the noise. If you're too global, maybe you will be too smooth and not be able to adapt to the structure of the data. So we need to try different values and use the validation set to find the best one.
So for instance, if I go back to just to 1, because it was like one corner case, we have this very weird decision boundary on and that's our training set. And I can check the score on the training set, and of course I get 1 because I learned the distance like of all the all the data
it's a question. Try to think why it's when you have n neighbors equal 1, why the model is making perfect predictions. Try to think how the model works internally. To make a classification, it will find the nearest neighbor, and the nearest neighbor is itself. So it's going to find its own true classes. So because we are evaluating on the training set, we just memorize and do a query in the database and we find ourselves and we make a perfect prediction each time because we just have a perfect memory of the training set. But then on the validation set or the test set.
So you can already make the plot and check how only seeing the test data, how they are on the boundaries. So already we see that probably here we have like a very, let's say, complicated boundaries, decision boundary, for probably not specific reason, okay? It's because it was only noise, and we just make this specific decision there. And for instance, here we do like coming back, and this point is classified on the blue line, not for, just because of noise, okay? So, and then you can check the score, and you get 0.76, which is already better than the linear classifier. But then you can increase and check how it generalizes. So here we obtain a line. In that case, because we have more neighbors, we make even errors on the training set. But when we look at the decision here, it's more meaningful. And if we check the score, we make a bit less errors on the testing, okay? Because we are able to, through regularizations, to improve a bit the results. Okay.
So there's basically a trade-off between model flexibility. So if the model is too flexible, it will memorize the noise. But if the model is too constrained, too smooth, then it might not be able to capture the interesting part of the distribution of the training set. And so there is this trade-off in model complexity. And most of the scikit-learn machine learning models, they have some hyperparameters that can control the complexity, the flexibility of the model. And we need to adjust that to find the best value.
Okay, so now the exercise is to load the iris dataset, because now we are playing with blobs. So load the iris datasets, play with the number of neighbors, and check what's the best trade-off. By splitting the data into training, testing, and checking what are the results, what's the best there. So yeah.
So you can choose an arbitrary train test split, like for instance, 80% for the train set and 20% for the test set, and train k-nearest neighbors on the training set and score it on the test set, and print the score both on the train set and on the test set to compare the influence of n neighbors, and find the best value of n neighbors on the iris dataset. Okay? So it's a recap of what we've seen previously. So let's have 5 minutes. One question, yeah?
I think it will help with the...
Okay. Okay. So I will load directly the solutions. So we already saw that we can load the iris dataset from Scikit-Learn. We load also the module to make the train test split. So here we get the X and Y, okay, and we put the data in X, the target in Y, and we split our data by taking 25% for the testing and the complement for the training. Stratify over Y to be sure that we have the same proportion everywhere. And here it's coming back to the question that we had before on splitting data to train validations and testing. So when we want to make what we are doing right now is trying to optimize the NumPy parameters. So we need to have the testing completely separated that we never saw to actually see the performance of our final models. And what we'll do is resplit the training into a train and the validations and to evaluate the influence of the K on the validation set. So here we split to train and test, and here we further resplit the training into a validations and a sub-training, okay? So you see that basically you have these things here, train val and the test, okay? It's just, that's why we have like 3 things. And now, what we are doing is for different value of the neighbors, we will compute the train score on which we just fit our KNN on the train sub, so on this X train sub and Y train sub, and score on the train sub in that case, and we'll check the validation score on the validation set here, okay? And
why is it X train and Y test? Okay. Sorry, it was just off the screen.
okay, so because this one will be totally at the end when we find our base neighbor. So
what is the test size for seconds?
yeah, let me. So we did half and half.
Yeah, because this iris dataset is very small. Here we use a large test size, and the training set is going to be small in the end. So here it's the proper way to do it. But on such small dataset, we would also need to do what we call cross-validation to be more efficient with respect to the size of the dataset. And this is something that we will introduce later this afternoon.
So here I just split everything. So here we split twice our data to get training, validations, and test. And our inner loop is to evaluate the influence of K and to find what is the best K that we can find. So we train the models, and then we evaluate on the validations, and we make a loop for the different K. So we get like 20 outputs. And now the idea will be to find what K is maximizing basically on the validation sets. Okay, we don't care about the training sets. It's just to see if training is actually if the testing is generating on the training. But what we are trying to maximize here is the second number. So basically the accuracy that we get on the validation sets. And the optimal K that we found was probably 9.
No, it's not.
I don't know exactly why it's 9, but
so yeah, in this case it's weird because K equals 4, you have a good one.
K equal 2.
K equal 2 also, and also this guy, 12. So there is a good region of good K's here and a good region at the beginning. And it's quite unusual, but it's probably because we have the random train split, and maybe when Andreas wrote this notebook the first time, 9 was the best one, but it's no longer the case. And this is it's really an artifact of the fact that we have a very small data set. So it's not stable to find a good k here in this case. Apparently, you can say k equals 12 is good, or k equals 1 is good, or 2 is good. That's kind of unusual. If you have a larger data set, it's likely that there is a region of k that is good, and most of other values will be slightly worse.
So now that we found out, or that we think that we found our best neighbors, I mean numbers of neighbors, we create a new classifiers, and now we'll fit on the whole training sets. Okay, so training plus validation together, and now we will predict on the set that we completely didn't use up to now. Okay, because we already optimize the parameters of our models. Okay, and now, yeah, here is 2. And now we find that our accuracy is 0.947, which is a bit lower than what we found on our validation, but it doesn't matter because our set is too small. Okay, that's. Yeah. But here, this is by hand how you would do to search an IP parameters. So, for instance, when you have models, you have several parameters, and sometimes you want to find the best K, the best C for the logistic regression, etc., etc. And this afternoon we'll see that you can do that in Scikit-Learn just by a single line, not doing the for loop yourself, okay, and avoiding that you mess up with basically the split of the data, okay? So you just give the data, you say I want to optimize these parameters, and then you will make the splitting for you. But under the hood is what it's doing, and is a good exercise to see, okay? Do you have any question about?
Maybe what you can do is change the random seed here for the two splits. Put 1 and 1, for instance. 42. And see if the location here. So we see that the top, actually, now in this case, K11 is even better. But it's really weird that the validation accuracy is larger than the training accuracy. It's because those datasets are so small that we cannot trust those numbers. Basically.
So don't do machine learning with 150 samples. That doesn't work. So yeah, we get better results. Non-significant. Okay. Do you have any question on that? Well, it seems clear. Yeah? Okay, so we can move to the next notebook, which is supervised, but in that case, we'll focus on the regression instead of the classifications. So up to now, with the classifications, our target was a category, spam, non-spam, which type of flower, which species of flowers. So now it will be a bit different. It will be a continuous variable, so predicting the temperatures or the humidity and this type of things. So we'll see that basically this is the same strategies. It's just that our output and our score, we will evaluate with different metric. So we import matplotlib and NumPy. And now we'll create x, which will be between -3 and 3, okay? And we want 100 samples which are equally spaces, okay? That will be our x value. And then we will create a y, which will be a sign of the 4x plus x plus a bit of noise, okay? So we create y, and now we can plot the relationship between x and y, okay? So what we have is, we have our x, which is going up, which is increasing, and then we have our sign, which is added to this x, okay? And then fluctuation for the noise.
So there is a linear trend plus a local periodic variation. So it's global warming, summer and winter. So in this case, you see that y is linked to a single variable as an input. So the target variable y is linked to a single feature, basically. So here it's a bit of a very specific case where we have a single feature in the input space.
So one way of doing regression is to actually use ordinary least square to actually find how x and y is just related. And as Olivier mentioned before, one thing that we absolutely need in Scikit-Learn is that our x, our big X, so our data matrices need to be a 2D data. And here is the case that we have only a single features. And to transform these 1D matrices into a 2D, we can create a new axis using np.newAxis, as we saw in the NumPy introductions. Okay, so if we do that, we see that we go from a single array of vectors of 100 numbers to an array, a 2D array of a column with hundreds lines. Okay, 100 rows. So the same way that we did for the classification, we can split into a train and a test our data with the same functions. So here I will just jump a line. And here we decide that our test set will be 25%. And random and here stratify don't apply. Okay? Because we have a continuous variable. So we can split our data. And the same way that we were doing before, we can fit a linear regression which will learn how to fit these lines. So we create a regressor with linear regressions and fit X train and Y train. So as before, we have some coefficients. So here it will be the slope of the lines, because we will try to fit a line. So it will be a slope of the line plus the intercept on the y-axis. And basically we can draw this line, okay? Because there's the weight multiplied by the inputs plus the intercept that we found. And if we plot that, is what we obtain. So that's our real data. And the line that we just found is basically the line that across like the data in the middles. So you see that basically with linear regression here, we are not able, simply with the data that we are not able to find the non-linearity of the sign, okay? We find the linear trend of the x, but we don't find the non-linearity. So is what we can basically predict and check our predictions. And we see that when we predict, the prediction correspond of the point which are basically on that line, because it's a linear regression. Okay.
So here we are making predictions for each of the x values in the training set.
So this point, like the blue point, basically we create a point here.
So the blue points are with the true target, and the orange point are the same x values, but the output is the output of the model. So the y value is the output of the model. And so you see that everything has been projected to this line. And what the ordinary least squares model linear regression does is trying to minimize the distance between the orange point and the matching blue point, the difference taken to the square. And you take the sum of all those square differences, and this is what we call the least squares model. And it's trying to find the coefficients for the linear trend that will minimize the sum of the squares.
So that's why your straight line is exactly in the middle of the sign, because it's what minimizes the distance between every point, okay? So that's more or less because it's a bit of noise. So now you can predict the same way on some new data, and you will see exactly the same things that the point that we didn't predict, we will predict them on the same line, okay? So a way to evaluate in that case will be so we saw that for classifications we use accuracy. In the case of regressions, we are using the coefficient of determination, so it's a R-squared score. So when we go regressor.score, because this is a regressor, in that case it will output us this score, where 1 means that all the points are well predicted, and then it will go to -infinity when this is not well predicted.
So here it's a bit misleading because here this formula is for the mean squared error, which is an error. And here this is a score. See, this is the R2 score. So a score in Scikit-Learn is something higher is better. And here we know that for the R2 score, a perfect model has a score of 1, a random model has a score around 0, and a model that has been really badly designed and predicted very anti-correlated stuff would be negative values. And the mean squared error is actually the function that the linear regression model is trying to minimize. It's trying to minimize this objective. Maybe you can import it from Scikit-Learn metrics. MSE, or mean squared error. Non, fait juste mean squared error of y true or prediction and y test and then prediction.
Yeah, but I don't have the y test. Ah, yeah, okay. Sorry,
test, okay.
I didn't.
I think it's y test first.
Yeah, it's the true first.
In that case, it's symmetric, so it's not a problem. But in general, in Scikit-Learn, for the metrics, we put the true value first and then the predicted value second. So here, this quantity, we try to minimize it, and a perfect model will be 0 error. This quantity here, which is the R square, we try to maximize it, and the perfect model will be 1. We'd have a score of 1. We could also have additional metrics like the absolute deviation, mean absolute deviation, or other regression metrics. We will see more, I think, this afternoon, mean absolute error. Yeah.
So, yeah, the advantages of those type of errors, so the R square, they are not linked to the target that we use. So, for instance, when you use the mean absolute error, it means that this is the error that you do. For instance, if you measure temperatures in degree, this mean absolute errors, it's in degree as well, okay? So it's linked to what you are measuring. So you can interpret it as a human. The R square is just the distances to what you are like basically regressing, and this is more difficult to interpret.
There's no direct interpretation because you cannot see the dimension of.
But yeah, the notebook on the metrics this afternoon is just like focusing on that. So we'll come back. So here it's just more to see that in classification, score corresponds to accuracy. In regression, score corresponds to this coefficient of determinations, which are also called R square. Okay. So now there is an exercise in which we'll try to make our linear regression a bit smarter by succeeding to predict, to account for the non-linearity. So to do that, we need to concatenate a sign of 4x in x. Okay, so we'll add the second column. And there is explanation with how to do that with concatenate. And then to redo our building of splitting our data and see how our fitting and predict changes. And we'll see that should be better.
So the goal of the exercise is to generate a new data set that has 2 columns. The first column is the same as previously, and the second column is sinus of 4x. So we compute the sine function on 4 times x, and we store the result in a second column. So to concatenate 2 columns, you can use this function from NumPy. And then you redo the splitting, you retrain the model, and you see whether or not you can make better prediction this way.
Bless you.
Okay? And basically, because the model is linear by nature, we can do nonlinear feature extraction to kind of remove that limitation of the model to find a better prediction.